Welcome back to Part 8. Up to this point, we have successfully constructed the complete qualitative logic structure of our reactor vessel fault tree. Every failure pathway has been systematically traced from our top event, G explosion, down until it terminates into a defined basic event. Now that our system logic is fully mapped, we are ready to transition from a qualitative structure to a quantitative analysis. However, before we begin entering numbers into the item toolkit, we need to take a brief step back from the software interface itself. To ensure our calculations are mathematically sound, we must first look at how we categorize our basic events under two fundamental risk analysis frameworks: demand-based failures and time-based failures. Not all components fail in the same way. In this section, we will break down the crucial distinctions between these failure categories so that you can select and apply the precise mathematical models required by the toolkit's calculation engine. Now, let's examine the first major conceptual slide, which defines the two overarching categories we use to classify our basic events before quantification. As we can see on screen, these are demand-based failures and time-based failures. The first category, demand-based failures, applies to components or subsystems that remain in a standby state during normal operations. These components do not continuously run. Instead, they are called upon to act only when a specific system trigger or hazard occurs. Because they sit idle, we are not measuring how long they run before wearing out. Instead, we are looking at the probability that the component will fail to change states or perform its intended function at the exact moment it is requested. A classic example from our system is the human operator. They sit waiting for a runaway reaction, and we measure their probability of failure based on that single instance of demand. The second category, time-based failures, applies to systems, lines, or components that are continuously operating throughout the mission profile. For these elements, failure is modeled as a function of operational exposure time. The longer a pump runs, a sensor reads a line, or a valve handles active flow, the greater the statistical likelihood of an unexpected failure due to wear, fatigue, or environmental degradation. By separating our basic events into these two distinct groups, we can ensure that we pick the correct mathematical input profile when we step back into the item toolkit interface. Let's take a closer look at the mechanics of demand-based failures. As we established, when a component is in standby, we don't look at a continuous failure rate over time. Instead, we measure its reliability using a static probability value. This is typically expressed as the probability of failure on demand. In a basic, deterministic analysis, we assign a single, fixed probability value to this event, for example, stating that an operator has a 1 in 100 chance of missing an alarm. The calculation engine takes this exact number and propagates it directly up the tree. However, in real-world risk engineering, numbers are rarely completely certain. That brings us to the concept of uncertainty analysis. In a fully realized probabilistic risk assessment, instead of a single fixed probability, we place a statistical distribution, such as a log normal or beta distribution, on top of that probability. This allows us to model our engineering uncertainty and state a range of possible values rather than just a single point estimate. While executing a full uncertainty distribution analysis is an advanced topic that falls outside the scope of our introductory reactor vessel example, it is a vital concept to keep in mind. Understanding that these static probabilities often represent the mean of an underlying distribution is what separates basic modeling from advanced, defensible risk analysis. Now, let's pivot to the details of time-based failures. Unlike standby components, continuously operating equipment requires us to model failure as a function of time. To do this, we use time-dependent probability distributions, most commonly the exponential distribution for constant failure rates, or the Weibull distribution when we need to account for wear out or burn in periods. Just like we saw with demand-based failures, we can also perform an uncertainty analysis on these time-based models. However, there is a fundamental difference in how this is structured. Instead of placing a statistical distribution directly on top of a final probability value, a time-based framework applies the uncertainty distribution directly to the underlying parameters of the time-dependent model. For example, if you are using an exponential model, your key parameter is the constant hourly failure rate, denoted as lambda. Instead of treating lambda as a fixed number An uncertainty analysis treats lambda as a random variable governed by its own distribution, such as a gamma or log normal distribution. The calculation engine then samples from this parameter distribution over time to compute the overall system unavailability profile. While we will continue to use fixed, deterministic values for our reactor vessel case study, understanding that uncertainty targets the model's parameters rather than its final probability is essential as you transition to more complex, time-dependent risk profiles. Now, let's explore the single most widely used time-based model in probabilistic risk assessment, the constant failure and repair rate model. When a system or component is continuously operating and maintained, we often assume its underlying failure mechanisms are purely random. This means the component has a constant probability of failing per unit of time, regardless of how long it has already been running. In reliability engineering, this constant failure rate is designated by the Greek letter lambda, usually expressed in failures per hour. But failure is only half of the life cycle equation. Because these components belong to a maintainable system, we also introduce a constant repair rate, designated by the Greek letter mu. The repair rate represents the frequency with which a failed component is successfully restored to an operational state, typically derived from the mean time to repair, or MTTR. When we combine a constant failure rate with a constant repair rate, the component reaches a state of statistical equilibrium over a long mission profile. This equilibrium allows the calculation engine to compute a stable, steady-state unavailability. Now, let's look at how the probability of finding our component in a failed state changes as a function of time. When a component first starts operating at time zero, we assume it is in a perfectly working state, meaning its initial unavailability is zero. As time goes on, the component runs the continuous risk of breaking down based on its failure rate. However, because this is a maintainable system, our repair teams are also actively working to fix failures based on the repair rate. If you look at the graph on screen, you can see how these two competing forces interact over time. The curve starts at zero and rises sharply at first because failures are occurring. But as more time passes, the rate of new failures begins to balance out with the rate of completed repairs. Eventually, the curve completely flattens out and hits a plateau. This flat portion is what we call steady-state unavailability. It represents a state of statistical equilibrium where the system's risk level stabilizes at a constant, predictable ratio. For most long-term mission profiles, this steady-state baseline is the primary value we use to understand our long-term system risk. Now, let's explore another highly common time-based failure framework, the dormant model, which is often referred to as the hidden or unannounced failure model. Unlike our continuously operating subsystems that instantly alert us when they break down, a dormant component sits quietly in standby. If it fails while sitting idle, there are no immediate operational symptoms, alarms, or indicators to tell us that it is no longer functional. The failure remains completely hidden or dormant until one of two things happens. Either we perform a periodic inspection test, or a real emergency occurs and the component fails to respond on demand. Because these failures are unannounced, we cannot rely on a constant repair rate to automatically kick in. Instead, the probability of finding the component in a failed state grows continuously over time. The longer it sits uninspected, the higher the likelihood that an undetected fault has occurred. To manage this hidden risk, engineers implement periodic testing intervals. During a scheduled test, the standby system is intentionally activated and checked. If it is found broken, it is repaired and restored to a perfectly working state, resetting our failure clock back to zero. When we model this in risk analysis, we look at the average unavailability between these inspection windows. Understanding this model is critical because it directly proves why regular maintenance testing is mathematically necessary to prevent hidden faults from compromising our safety margins. Now, let's look at the graph on screen to see exactly how unavailability behaves over time for a dormant component. Unlike our active systems that plateau into a steady state, a standby component with hidden failures displays a completely different pattern. When the component is first placed into standby at time zero, we assume it is fully operational, so its unavailability starts at zero. Because any failure that occurs while sitting idle goes completely unnoticed, the probability that the component is broken grows continuously. On the chart, you can see this represented as a steadily rising line or curve. The longer the system is left alone, the higher that line climbs, and the more exposed we are to danger if an emergency demand occurs. This upward risk trajectory continues until we hit our scheduled inspection point, known as the test interval. At this exact moment, a technician tests the system. If it's broken, it gets fixed. As you can see on the graph, this maintenance action causes the unavailability line to instantly drop straight back down to zero. As soon as the test is complete, the cycle repeats. The line begins to climb again until the next scheduled test drops it back down. This creates a distinct, repeating sawtooth pattern. To wrap up our theoretical discussion, let's quickly summarize how the basic events in our reactor vessel model map to these concepts before we transition to the software. When we look at our system layout, almost all of our safety hardware components, such as the sensors, the controllers, and the emergency valves, spend their time sitting quietly in standby. They do not experience active operational wear. Instead, they are waiting for a runaway reaction to occur. Therefore, we will be using the dormant model for these physical standby components, managing their hidden risk through our scheduled periodic testing intervals. Similarly, our human error element, the operator response, or OP, is a demand-based failure. The operator isn't continuously failing over time. Rather, they are called upon only when an emergency hits, meaning we model their reliability as a static probability of failure on demand. The single exception to these standby frameworks in our example is the main power supply grid. Because the grid is continuously active and maintained to provide baseline power to our system, we will model it using the constant failure and repair rate model. This allows us to track its random failure likelihood balanced against how quickly it can be restored. By establishing these precise definitions up front, we have built a solid foundation for our quantitative analysis. In Part 9, we will jump right back into the item toolkit interface, open up our basic event table, and physically assign these exact failure models and parameters to our logic tree. Thank you for watching, and I'll see you in the next section where we make our model fully quantitative.